for the weaker forms, we have a complete solution which might be interesting to all of you, and it's also interesting if whether you are an algebraic geometer or a geometric topologist or a group theorist. And it's really easy to state. It's really just something that you can draw in a few moments, at least state the conjecture. All right, so the story, let me tell, I mean, as I said, the conjecture came up several times over the last 100 years. And so let me give you one intuition of where it comes from. This is PL topology. And by the way, everything that I'm talking about is part of a joint work with Professor Igor Park at UCLA. You can look it up on the archive. I don't remember the title, but I mean, I don't even remember the title that I gave today, but I want to talk to you essentially about the Alexander and Oder conjectures. Okay. So here's the first way of stating it. All right. So let's say we have two polyhedra. We can assume that they are nice manifolds, but let me not for the moment. So we have P and Q, and these are some polyhedral spaces. And all I know for the moment is that they are related by a PL homomorphism. So a homomorphism that I can realize by a piecewise linear map. Okay. So P and Q, polyhedra. If I should write larger at any point in time, let me know. You also get that. And this is they're related by a PL homomorphism. All right, so phi, it's a PL homomorphism. All right, so this is like a map. All right, there's not only continuous homomorphism, but I can realize it as a piecewise linear map. Okay, so simple enough. Okay, so now you can ask yourself, can I in some way factorize this map? Can I write it down in a simpler way? All right, can I write it down in terms of some local operations, let's say? And it turns out that this is true. So classical. In this case, P and Q are related. P and Q are related by some sequence of bistellar moves. A sequence of stellar subdivisions at inverses. Okay, so again, I said everything can be relaxing and can be drawn on the blackboard. I mean, at least a low-dimensional picture. So let me give you an example of two polyhedra that are kind of related by a pure homomorphism, and it could be this, right? I mean, these are two triangulations of the same disk. All right, it's a two-dimensional disk. Okay. And now I claim that they are related by something called stellar subdivisions at inverses. So what is a stellar subdivision? Well, okay, so a stellar subdivision so I take a simplicial complex, right? So I have, so what do I do? Input. So operation. So input is delta simplicial complex and let us say sigma in delta simplex. And so what I want to do is, okay, so let me first draw some of the kind of the visual picture. All right, so we do it like this. So this is my simplicial complex, and here I take a simplex. Okay. Now I chose a simplex. So now what I do is I remove every single simplex that is incident to the chosen simplex. Okay. So what are the incident simplices? Well, it's the simplex itself and these two. Okay. Everything. Let me just say. I mean, I have a simplex. I mean, a simplicial complex you can think of just as a downclosed collection of a finite set. All right, it's a downclosed subset of the power set of a finite set. And then I'm basically taking a simplex and everything that contains it. All right, so this is somehow the downclosed set would be here on, would be the downclosed set on 1, 2, 3, 4. The simplex I chose would be 2, 3. And then I choose every simplex that contains it. So it's 2, 3, 2, 3, 1, and 2, 3, 4. Okay. So what do I do? All right. So first step, remove sigma and every simplex of delta containing it. Containing sigma. All right, so I removed. All right, so let me call this for the lack of a better word. I denote it like this. So I call it the star or the open star of sigma and delta. All right, I remove that. And now, so now I changed the topology, right? If I remove those, then of course I change the topology. All right, the new topology would be a circle. That wouldn't be good, right? I want to stay in the same topology. So what I then do is I want to fix it up again. So the next step is I add the cone over the hole that I left. Okay? Consider the union with the cone. So I take a new vertex that I introduce artificially, and I take the free join over the boundary of the hole that I just left. All right. So I have this hole that I left here, all right, and I introduce a new vertex, and then I cone over this, and I obtain something like that. Okay, so this is my stellar subdivision. I take out, and then I basically fix with the cone. Simple enough, right? So, and now we can understand the statement, right? So if P and Q are related by this pair of homomorphism, then they are related by stellar subdivisions and inverses. So I can take a stellar subdivision. I claim I can go take a stellar subdivision from here and go to some other object, and then I maybe have to take the inverse of a stellar subdivision, right? So I apply not the stellar subdivision, but the inverse operation, and at some point I will get to this object. And in this case, it's rather simple, right? I mean, I could take, right? I take the stellar subdivision here, and I end up at this object. But I can take also the stellar subdivision of this object at this edge, and also end up here. All right. Okay, so that's the nice thing. And this theorem by Alexander and Newman, so this had been proven several times, is that if P and Q are related by a PL homomorphism, then they are related by stellar subdivisions and inverses. Okay? And now the question or conjecture, depending on which paper you look at, that was asked. So I think Alexander formulated it as a conjecture, a hopeful kind of question was whether we can do something that happens in this picture. And this means, what did he ask? Well, he asked whether we can put all the subdivisions first and then put all the inverse subdivisions. Or in other words, okay, so can we put all stellar subdivisions first, and then apply the inverses. Okay? Or in other words, right, I want to go from P, I do a subdivision, I do something, right? A subdivision makes me finite, introduces a new vertex. I go up, I reach some object, let me call it M for the moment. And then from here I go back down. I do somehow, right? From here I go back down to Q. Or in other words, okay, so is there, another way of saying it, is there this object M that is this joint refinement under the stellar subdivision? So is there this object M that is obtained as an iterated stellar subdivision of P and an iterated subdivision of Q? Okay? And you can ask this in several categories, right? In several forms of strictness. You could ask this on an abstract level, on a purely abstract level of combinatorial objects. And then you can ask this on the level of geometric objects, right? You can ask this, do you have a geometric complex realized in some ambient vector space? In some rational vector space. And then you put the subdivisions in a geometric way there. And this question becomes a little bit different, but and then you can ask an even more strict question, and I want to go to the strictest form of the conjecture, and this comes from algebraic geometry. Okay, so at some point, algebraic geometers kind of rediscovered this business. I don't know how. So I'm not very good with the history. You can probably ask Crochet. But at some point, there was this is kind of this PL topology of 100 years ago up to the 70s, but then at some point algebraic geometers became interested in something related. And what they wanted to do, well, they looked at varieties that they knew were in some way related. So in the same way that we knew that there's a PL homomorphism here. And one way of thinking about it, you could look at, for instance, varieties that you know are birational. Okay? And then you can ask yourself, well, okay, so X and Y are birational. All right? Under which conditions are they related by these kind of moves, by kind of local moves, by analogous moves? What would be the analog of the stellar subdivision? Well, the stellar subdivision would be corresponding to a blow-up. Okay? So stellar subdivision is a blow-up, the inverse. Okay, so the inverse, the blow-down is the inverse to a stellar subdivision. Okay, that's what you should think about. And in fact, you can really think about it this way if you go to toric varieties. So this is some other question that you can ask yourself. All right, so under which condition, under which conditions do I have a common blow-up, right? So I have X and Y birational. Does there exist X. So a new object Z that is a common blow-up. All right? And if you look at toric varieties, so if X and Y are toric, then you can indeed think of this really just as this geometric picture. All right? I mean, it's not really clear that you can go from the general picture to a toric picture. Okay, that's a little different. But now, let's say we have a toric variety. So a toric variety is, right? Okay. So let me just think of it as a simplicial fan. All right, it's a collection of simplicial cones that cover my ambient space, and these are all rational cones. Okay, so this is one toric variety, and here's another toric variety. And now I can ask, well, can I go from is there a common blow up? Now, usually what we want in this case, all right, the strongest form that we could ask for would be that we do the blow ups at smooth centers. So what is a smooth center? Well, okay, so let's look at the lattice points here. All right, so this is a rational fan. So these are kind of the lattice points here. And so when I'm saying that I want to look at the smooth center, I'm looking at the primitive lattice point along a ray. So for instance, here's the first lattice point along this ray. This is the first lattice point along this ray, and then the barycenter would be the sum of them. Well, this isn't quite as like a parallelogram, but this would. Okay, so this would be. But why do I introduce a special point? Well, remember that I introduced the stellar subdivision here. Right? I had the stellar subdivision, I introduced a new point. Right? And I mean, I placed this point anywhere. I didn't really restrict. But if you are talking about toric varieties, and you want to blow up at the smooth center, then you're basically only allowed to introduce this point at this new location that is prescribed in this fashion, right? I take the primitive lattice points, and I take their sum. And this is the point, this is the location. So this is V sigma when I subdivide it at sigma. So you see that there's a slight more restriction of where I put the points, all right? So this is more restrictive. And now you can ask yourself, well, I mean, okay, so if X and Y are toric, does there exist Z toric such that, okay, so let me say same support or birational such that does there exist Z toric such that X blows up to Z at smooth centers. And Y blows up to Z at smooth centers. So this question here is sometimes called the order conjecture. So it's a form of this Alexander conjecture due to Tadao. Okay? And we don't know that. So let me just state the theorem that we can prove. And let me be clever about at least slightly clever about using space. Theorem, and this is so Pack. And again, it's an archive paper from this year. I forgot to write down the archive number, but you can find it or you can ask me. So what is the theorem? The Alexander conjecture is true. It's true. And we don't know the order conjecture, but we know the weighted order conjecture. So instead of putting these points at the smooth center, we put them at the rationally smooth center. Okay. And the weighted or rational order conjecture is true. We don't know about the the algorithm does not give us. The algorithm does not really extend well to the smooth case, so we don't know. It's a wide open question. Okay, so good. And now I want to sketch at least and give you an idea on how this goes. Okay. Any questions up till now? No.
So is this weighted order conjecture special case or the order conjecture?
It's a special case. It's weaker. It's a so in the smooth order conjecture, the strongest form of the order conjecture, when you do a stellar subdivision, yeah, every time you do a stellar subdivision in the span, you're allowed to introduce the location where you introduce this new point, V sigma, right? So there was this from here to here, introduce a new vertex, right? And the location is basically prescribed to you by the geometry. Okay, so in this situation, all right, it was easy to go from here to here because I could basically just take the common intersection of these two. But imagine that for some geometric reason, V sigma was forced to be at this equation. Okay, and then you would, then it would look like like this. But this object is now not a stellar subdivision. So that's the issue. So there's a kind of geometric restriction that comes in from basically, I mean, if you want it, this is just smoothness forces. Okay. I mean, let me not go into the full business of toric varieties. It's not really interesting, but that's kind of the underlying point. All right, good. Huh? And, okay, so the Alexander conjecture I take as the abstract one. So you take abstract polyhedra, and then you do combinatorial operations. This here is kind of the geometric one. So the first point is a consequence of the second, right? So yeah. So Alexander conjecture is the abstract one. I didn't really talk about what it means to do all these things abstractly, but just up to combinatorial. But think of this, I mean, what I will discuss now is really the geometric picture, which is the second one, it's stronger. So what I will discuss now is the argument for this, and it implies the first one. Okay, thanks. Good. All right, and I want to give you basically an intuition of how things go. So really, I mean, another way of thinking about this is that we have presentations of some object. So let's just think about group presentations for a second, right? Let's say we have two presentations of the same group. And okay, so then you can ask yourself, are they related by some elementary transformations? And sometimes we know these things, right? We know that already there's an elementary way to go from one presentation to the other. And now we're asking ourselves, in some way, can we reshuffle these moves? And in the end, the proof relies on encoding this as a kind of combinatorial, as a problem on words. And so this intuition is not entirely stupid. So let's make some simple examples, okay? Let me introduce some notions. And okay, so let me stay for a moment with the two-dimensional picture. So intuition for proof, and I will stay in the two-dimensional picture. Two-dimensional picture. So, all right, so I have two subdivisions of a polygon. All right, so I have one polygon, and another polygon. And I want to show that these two have a common stellar subdivision, okay? And I want to try to illustrate what happens. So first of all, I introduce a notion of a special kind of polygon, and this is called, I will call a fin, okay? You can see that we came up with part of the proof, at least when we were in a seafood restaurant. If you're very good, you can guess what we had. So we call a fin is, okay, let me do it the following fashion first. Okay, so a fin is a triangulation of a polygon Q exhibited with a distinguished vertex, vertex V. All right, so here I have a vertex V. So it's just really, it's just a triangulation with a distinguished vertex. Okay? So I have my vertex. Let me not make a too nice picture. Let me do it like this. Okay, so this is all right. So I have a distinguished vertex. And now so now I look at the horizon, the definition, horizon of the fin Q with respect to the distinguished vertex. Well, this is minimal subset of the boundary of this polygon such that the underlying set of the horizon V of Q is equal to Q. Okay? So basically, I just want to have this boundary here, right? This part of the boundary, because once I cone over this part of the boundary, I get my polygon back. Okay? Simple enough. Okay. The fin I call scaled if, okay, so what do I know? What do I want? So I have my map from, I have my horizon, right? I have Q, and I have the horizon of V and Q. And now what I want to do is I want to just do the radial projection from V. Okay, so I remove V. All right, and every other point in my polygon has a radial projection onto this horizon. Okay, so if I take this point here, I can just radially project it onto the horizon, like this. Okay? And this maps me, okay, so this maps the simplices. Okay, so this maps the simplices of Q. It maps them to subsets of this horizon. Okay? Yeah? I'm staying in the plane. I'm trying to give you an intuition of how it happens. Okay, so this is, for now I'm staying in the plane. Okay, and if I have time, I will try to explain what happens in high dimensions. But I'm trying to just give you an intuition, and everything now is in the plane. I'm just really looking at polygons. Okay? Yeah. Thanks. Okay, so I take simplices of Q to subsets of this horizon. But they are not necessarily simplices. All right? So I have this. Okay, so what would be an example? If I take, for instance, the image of this simplex here under this radial projection, it's a collection of two simplices. Okay? I could also take, maybe, let me make this subdivision here. If I take the image of, let me make it a little bit, let me make it a little bit small. Let me make it a little bit clearer. It's always, so this here. Now, if I take the image of this simplex under the radial projection, it will be some subset of this simplex. All right? So the image is not always a simplex. So I call a fin scaled if the image of, so this radial projection, let me call it rho or v. So the fin is scaled if v maps simplices to simplices. Okay? Let me make an example of a situation where this goes well, and this may be more instructive than just writing down the definition. So I have my vertex V. Now like this. Okay? So they claim that this object is scaled. This is a scaled fin. Why? Because, right, I mean, I can draw once again the same color. Clever. The horizon. And if I look at one of the simplices here, let's say this one, under the radial projection, it maps to a simplex of the horizon. Okay? Simple enough. Okay? Good. Okay, so I mean, let me stay for the convex in the convex setting. Or I mean, what we need for the moment is that we are at least star convex with respect to this vertex V. Okay? And in the end, we will always be able to reduce to a saturation like that. Okay? But that's right. So, okay. Okay, for now, let me just discuss fins. And fins are star convex, okay? For now, okay, so for now, star convex, okay? All right. Now, I mean, if I write down the notion of a scaled fin, there's always kind of the simplest scaled fin that I can look at, and I call it the stripe. Okay, the stripe is really just the natural triangulation of the free join of V with respect to its horizon. Okay? So what would be the stripe? In this case, it would be just, I have the horizon, and I really just cone over it. it. So I have just this. Okay? So now, okay, so this is a stripe, this is a scale fin. This is a scaled fin, this is a stripe. And the claim is, and this is kind of the, I mean, if you want, this is kind of the main observation in the plane. The lemma or observation is that the scaled fin is a stellar subdivision of its stripe. So I claim I can go from here to here only via stellar subdivisions. Okay? Even, I mean, I don't even have to do inverses. There's really just one way of I have to go. Good. Why is that? And basically, I mean, this is basically, I mean, here's the only non-trivial or clever idea that happens also in higher dimensions. Or maybe that's not true, but I mean, there are some ideas. But here, there's something interesting happening. So let me do this. Let me do the picture in a kind of, and then we can do this together. All right, and I want to draw in a parallel way the stripe. Okay, that's it. I can go I can apply stellar subdivisions to go from here to here. Do you see how? Does anyone see how? How should I start? So which stellar subdivision should I apply until I look like this? Well, okay, so let me introduce the notion of an exposed vertex. So here, this is V. This is kind of the anchor point. This is where I want to go towards. And I call a vertex W in the horizon of my is exposed if there exists a unique edge E of Q such that E contains this vertex and E is not in the horizon. Okay, it's a simple notion. So this vertex would not be good because there are two edges here incident to it that are not in the horizon. Right? So this edge is incident to it, and this edge is incident, and both of them are not in the horizon. This edge, this vertex here is good. Right? Why? Because, well, there's this unique edge here. No, it's not in the horizon, and that contains the vertex. Okay? And now what do? Well, I pick this edge. All right, so I pick edge. So pick this edge E of W, and consider the opposing vertex. That's so Z, which is I remove exactly this edge. All right, so that would be the vertex here. It's kind of the opposing vertex. All right. So this is a point. All right. I can also find this point here. And now what do? I apply a stellar subdivision at this point. Okay. Now the next. Okay. So claim there exists always, and this is something that okay. So you have to be a little bit careful with the way you state it. that there exists always an exposed vertex. W exposed. Okay? So, I mean, this is a little subtle. What does it mean to be exposed, and also what does it mean to be exposed in higher dimensions? But okay, so let's assume that that this claim is true, that there's always an exposed vertex. So what do I do next? All right. So now I fixed the triangulation already in an area, right? So here, and here, the triangulations coincide, so I can forget about that part. I remove them. I'm still star convex, right? I forget about this part, but I'm still a star convex polyhedron. And now I claim that there's another exposed vertex in the new horizon. What would it be? Well, actually, there are several, right? I mean, now this somehow W prime would be exposed because this edge now is on the horizon. It's now on the boundary, right? So now there's a unique edge that is incident to it that is not in the horizon. And now what do? Is I introduce this. Okay, so I look at this vertex and I apply a stellar subdivision like this. Then I find another. Okay, so I remove this part. I forget about it. I find another one. Right, that would be the next one. And next one, and then I'm done. All right. So, I mean, there are some things here that are happening. So, but the important part is why does this always exist? Why is there always a way to find this exposed vertex? And it comes down to cleverly encoding some combinatorial word on this horizon. So let me do the way that the encoding works. So let me explain how the encoding works in the two-dimensional setting. Okay, let me just orient. So let me go back to the start. Right, I performed these stellar subdivisions. Let me go back to the start. All right, and tell you how to find the right encoding. Let me just orient this horizon in some way. Right, right, I look at this one. Okay, so now I go along this horizon, and I encode the edges that are incident to the horizon, and I'm looking at those edges that are that are not good for me. So there's always an edge that points towards. I mean, there's always an edge going from a boundary vertex towards this vertex V. Right, that's basically just coming from the definition of scale. But then there might be another edge. Right, there might be, if I go from here to here, there might be this other edge that is superfluous, that kind of prevents me from being an exposed vertex. And let me just encode it somehow. Let me just say that this edge has kind of this up slant. It goes, if I go from left to right, it goes up. Right? Okay, here there's none. Here there's so here there's a down, so it's a down, and then there's another down. Okay? It's up, down, down. Right, so up, there's a combinatorial word here, up, down, down. Simple enough. So when do I have do I have an exposed vertex? Well, exposed if I have a subword up, down, right? Or if I start with the down, or start with down, or end with up. All right, so these are the three conditions under which I have found an exposed vertex. All right, so let's assume that it doesn't exist. Well, then I have to start with a down. All right, I have to end with an up. Sorry, the other. If I start with a down, yeah. So if I have to, okay, so I have to start. I have to start with an wait a second. I have an exposed vertex. If I start with a okay, so I'm in a bad situation if I start with an up, all right, and I end with a down, and I have none of these up down in the middle. But if I start with an up and I end with a down, then somewhere in the middle I have to have this subword up down, and that's it. This proves that there's always an exposed vertex in this two-dimensional case. All right, simple enough. It's a very simple combinatorial analysis of what happens here. Okay, so this gives me, all right, so this very simple combinatorial analysis gives me already that the fact that somehow if I have a scaled fin, right, somehow a scaled fin and its stripe, then I can solve my problem. I can find the stellar subdivision of the stripe until I'm at the scaled fin. Okay, so I mean, okay, so this is a part of it, all right? So let me sketch on how this completes at least the program in the plane, how you get from this to the complete solution in the plane. And then, I mean, if I don't have time, which I don't, but you can ask me after over coffee, I will explain a little what happens in higher dimensions, okay? Let me try to give you an intuition of how you assemble this to an algorithm, at least in the plane. Sorry. Okay. So A and B are two triangulations or two simplicial complexes in the plane, and you know that they have the same underlying set. Okay? So they kind of look, okay, so let me make it something non-convex to make an earlier question happy. So this is somehow, okay, so this looks non-convex, but I can of course extend it to some convex triangulation. So I can find a polygon that contains these two, and I just extend the triangulation. So what I do is I can just find a larger polygon until they look the same. All right? And then there's the triangulation in the interior might be different, but now I have to find the common stellar subdivision. Okay, so I can assume convex. So let me make it simpler. So I have A and B convex, but neither of them are scaled fins. Okay, so A could look like this, and B could look like this. And now neither of them are scaled fins, but okay, they triangulate the same polygon, and I can take the same exposed vertex B. Okay, so now what can I do? Well, first of all, what I can do is I can turn them into scaled polygons, into scaled fins. And how do I do that? Well, the first step is okay. So let me turn A into scaled fin. So first step, scale A. Okay. So what do I do? Okay, so this is not scaled. So what I do is I look at the pullback of the horizon, all right? And because I know that, okay, so I know that this is not a scaled fin. There will be some transversal interaction here, transversal intersection here. Okay, I do just I perform a stellar subdivision at this. Okay, and I continue, and I'm done. Okay, so now this will happen again. I perform a stellar subdivision, another stellar subdivision, and now I'm scaled. Okay, so now A is scaled. Okay, second, perform stellar subdivisions. In B until B refines A. Okay, so I don't want to B to be a I don't want B to be a scaled fin immediately. I just want B to refine A. Okay, so I mean that you can find stellar subdivision until you refine this certain object. That's kind of an easy task. I mean, this is kind of, if you want, this is a really, I mean, again, this is a classical thing by Zeeman. Okay, so B refines A. So B in some way, B looks like a finer version of A. So B looks maybe like this. Okay. Now what do you do? So now, okay, so now I look at A. I know that A has an exposed vertex. All right, so okay, so I ignore the blue part. So this here would be an exposed vertex, and I look at this exposed region. Okay, so what happens in this exposed region? Well, it turns out that this exposed region is a stripe already, and B is a refinement of that stripe. Okay, so now I can work a little bit, and what I observe is since this is a stripe, there's a stellar subdivision of this stripe that coincides with the restriction of B to this region. Okay, and then I'm done. And go to the next part of the exposed region, and so on and so forth. Right? And in the end, I only applied stellar subdivisions on both sides. So in the end, I get a common stellar subdivision. And that's it. So the whole secret here is to basically look at these special kinds of triangulations, these special fins, find a combinatorial encoding, and find a reason that there's always an exposed vertex. And that's it. Simple enough. I wonder whether this can happen, whether in some way one can use this to address the integral version, the smooth version of the order conjecture as well. I don't know. I also made it a little simpler. I mean, this combinatorial analysis, what happens in the plane is really much simpler than what happens in higher dimensions. So you have to take this intuition with a grain of salt, but that's what the paper is for. But that's it. So this is what I wanted to talk about, and I'm happy to take any further questions. Thanks.
Okay. Thank you, Professor Adiprasito. And any questions from audience?
Okay, then you get a combinatorial array, and analyzing that is a bit more complicated. I mean, this is somehow, it takes more than 15 minutes to describe it. So we can set it over coffee.
Okay.
So when you choose the new vertex, I forgot what it's supposed to be called. For example, when you find the interior vertex,
yeah,
you wanted to do the stellar subdivision. Is there any requirement for the position, like where the new point you should be?
I mean, in this case, the new points. You mean this where I put this stellar subdivision here? It's kind of prescribed. It's. I mean, I look at this exposed vertex, right? It's incident to an edge, and then I look exactly at the opposite point here, right? This here, right? And this corresponds to a point here. And this is where I perform the stellar subdivision. This is the point I introduced.
So in the language of the fan, as you shown the example, when you choose the V sigma,
it's okay. So
it's kind of like precise.
Exactly. So that's the point where things differ, right?
Yeah.
So this point here might not be the smooth point, right? See, this is exactly where the algorithm breaks down if you want to do this over in the smooth setting. This here, the point that I introduce, might not be the smooth point. That's exactly correct. Yeah, that's a very good observation. Thanks. Does everyone understand what I'm saying? So here somehow the algorithm here forces me to basically introduce this point here, right? But this point in this edge might not be the barycenter of these two, right? I mean, this here is somehow it's prescribed by the triangulation on this side, but it might not be the barycenter on this side. So this is why the algorithm does not it doesn't really tell you anything about the smooth case. Again, this is where it breaks down. This is this is a key point. Yeah. Yeah. No. Yeah. It's known in dimension 1. So order conjecture is really, yeah. I mean, there's very little known. What is known is that we can toroidalize it up to dimension 3. So up to 3 folds, or I mean up to 2-dimensional simplicial complexes, we can. Right? I asked this question more generally. You have 2 birational varieties, and you can toroidalize in this you can toroidalize at least. You can reduce to the toric setting. That's known, but I mean the main thing now is the order conjecture in dimension for 3 folds, which is for the 2-dimensional simplicial complexes, or 3-dimensional fans. 2-dimensional fans, yeah, we know.
Okay.
One more question.
One more question.
Sorry about the polygon, the subdivision of the polygon. Are there any uniqueness about the subdivision of the polygon? I mean, so for example, A and B they both can like blow up to the same picture, but is this same picture unique if I choose some strategy?
No, it's not. I mean, it's not unique. No.
Okay, so even we can find some algorithm like from right to left or from left to right or from some criteria. It's still
Yeah. I mean, you can ask yourself whether there's a kind of canonical way of doing it. We don't know yet. I mean, we don't. I mean, probably there is, but.
Okay, thanks.
Any other question? Okay, let's thank our speaker again.